Hello, my name is Richard Porter and I work as the Principal Engineer for Advanced Solutions at Yokogawa, Australia and New Zealand. In this series of videos, we've been looking at common issues faced by the process industry and solutions that Yokogawa can offer. Today I'd like to start with a question I want you to ask yourself. Will your safety system keep you out of the news? No one wants to make headlines like these. However, if you've installed your safety system and never looked at it again, you're running a high risk that your plant will make front page news. In this video, we will explore the vital field of functional safety, and I'll show you how Yokogawa can improve your plant safety and keep you out of the news. First, I need to point out that it is a mistake to think that functional safety is solely about designing and building plant protection systems. That is a significant part of functional safety, but it is only part of the picture. Equally critical is what happens after the system is installed. The international standard IEC 61511 details how systems must be maintained and monitored, checks made to ensure the required safety level is not compromised, and that the performance of the safety instrumented system, or SIS, and plant behaviour match design expectations. Doing this manually is an enormous effort. The level of effort introduces a risk that people will not gather the information, the data will be incomplete, or the data will not be assessed and actions taken based on that assessment. Sadly, it is not unheard of for Yokogawa to be asked to reassess a safety instrumented function, or SIF, for a customer based on plant data that is incomplete. This commonly happens because the plant did not have a formal structure or tools in place to record the necessary data. Safety Function Monitoring, or SFM from Yokogawa, is a sophisticated software package designed collaboratively with end users to help them gather and assess the data and thereby meet their requirements for plant safety instrumented system maintenance and monitoring. The system I'll use to demonstrate SFM is a simulation of a typical depropanizer plant. The simulation includes all the elements that are part of a live plant and are arranged in the same way as would occur in a real facility. The process equipment and instrumentation representing the physical components are simulated in PetroSim. The instrumentation is connected using virtual I/O to the Centum and ProSafe RS controllers that are simulated using their own test software. The controllers are connected to an Exaquantum plant historian via OPC with the sequence of events recording and safety function monitoring applications on the same computer. The sequence of events recording, or SER, does event analysis and trip detection, while SFM provides visualization and reporting. For those unfamiliar with a depropanizer, the purpose of a depropanizer unit is to separate a mixture consisting mostly of butane and propane by making use of the difference in density of the two materials. Here we have a depropanizer column with feed stream coming in partway up the column. A reboiler heats the product to drive the process. The aim is to get the lighter propane to rise to the top as vapour and get the heavier butane to condense on the trays inside the column and drop to the bottom. At the bottom of the column, a butane-rich liquid is extracted and cooled. At the top of the column, the propane-rich vapour is extracted and condensed into a reflux drum. From the reflux drum, the propane-rich liquid is either extracted or pumped back into the column to remove heavier hydrocarbons. Following the safety lifecycle, a HAZOP study was carried out for the simulated plant and 5 SIFs were identified. The first 3 SIFs shut down the reboiler steam feed, while the final 2 SIFs protect against condenser overpressure and pumps running dry. The SIFs were then assigned safety integrity levels, or SIL, and configured in the safety controller application. Now we will simulate some events on our depropanizer unit. I'll start by simulating a valve failure on the butane outlet from the column. We see here the valve has failed open, and soon we'll see the sump level starting to drop. It takes some time to occur, so the video has been sped up. As the level drops further, it goes into alarm and then eventually hits the trip point. At this time, the inlet valves are closed. The SER is recording all events, and we can see the moment that this trip occurs. SER's trip detection engine identifies this trip, as well as relevant events associated with this trip required for safety function monitoring. Without any intervention, the situation develops further. The reflux drum level is dropping slowly. Once again, the process takes some time, so I've sped up the video. As the drum level drops, it goes into alarm and then hits the trip point, which stops the reflux pumps. SER shows the moment the trip occurs. SER's trip detection engine identifies this trip. The earlier trip which led to this is also shown. This is what we refer to as a parent-child SIF relationship. The parent, SIF 003, is the Depropanizer column sump level low-low trip, and the child, SIF 005, is the reflux drum level low-low trip. In SFM, we provide detail on the individual SIFs, as well as reflecting this parent-child relationship. This is the SFM Overview Page. The header has navigation on the left and status on the right. The filter pane allows us to customize the period directly or by selecting a layer of protection analysis, or LOPA phase. The filter pane can also be used to select the area of interest. Next to the filter pane is the main information pane. The first table shows the SIF overview, which lists the number of SIFs per SIL, the number of activations, and any output faults. The Depropanizer unit has 2 SIL2 and 3 SIL1 SIFs. There has been a single activation within the period and the area selected in the filter pane. There has also been a single output fault, which refers to a SIF failing to activate within the target time. The second and third tables show an overview of the status of the Independent Layers of Protection, or ILP, and the Maintenance Override System, or MOS. Navigating to the SIFs page shows us the list of 5 SIFs that have been configured for the Depropanizer unit. The version of the SIF is tracked, so if during the next LOPA there are modifications to the SIF, then this version number is incremented. The integrity level, number of activations, and output failures are also tracked for each SIF. The filter pane on this page also allows us to filter by SIF name. Moving on to the SIF activations page shows us the list of SIF activations according to the selected filters. Those activations with an output failure are highlighted with both a red row colour and a red traffic light indication. Traffic light indication is also used for Independent Layer of Protection, or ILP, verify and test. The ILP status shows if any of the ILPs for the SIF were out of action when the SIF activation took place. The verify status indicates whether the SIF activation has had a cause and effect assigned to it. The test status indicates whether the SIF activation has any actuating devices associated with it which have been marked as a test replacement. The parent and child SIF activations resulting from the valve failure on the butane outlet of the column are shown at the top of the list. There is an output failure on one of these activations, and neither have had an initiating cause assigned to them, nor have they been marked as verified. We do this by clicking the View button beside the column sump level low load SIF activation record. The details or effects of the SIF activation are shown on this page. The tabular data is for actuating device durations, such as the time taken to close valves or stop pumps, and their targets. The user's test is specific to the device, not the overall SIF activation. It marks this specific device actuation triggered by the SIF as a test replacement. The trended data shows the associated process and alarm and event data. This associated data will be trended for the period over which the SIF activation took place. The filter pane includes a Set Baseline button, which takes all process data for the current SIF activation and sets it as baseline or expected data. This means that every time this SIF has an activation, the baseline data will be shown with the trended data for comparison. The effects of the column sump level low-low activation show there are 2 activating devices, shut-off valves SDV3106A and B. The table tells us that the start time of the trip and that the target actuation time for both valves is 10 seconds. The close duration for valve A is 6 seconds, and this is shown both in the table and the chart. The close duration for valve B is 14 seconds, and again this is shown both in the table and the chart. Since this duration has exceeded the target, we have identified our output failure. After the valve failure has been investigated and repaired or corrected, we can take credit for testing this valve. This is recorded by selecting the Users Test button. Next, we need to assign the cause of the trip. We do this by first clicking on Causes in the header. This brings us to the cause verification page. We can select a cause using the drop-down and choose one of the predefined initiating causes for the SIF activation that were defined during the HAZOP. If the reason is not shown, select Other from the drop-down menu and enter the reason in the custom field. In this case, the reason is LCV 3101 outlet valve fail open. Enter the problem upset report reference number, which may be, for example, from a computerized maintenance management system, or CMMS. The assigned cause is then saved. The reflux drum level low-low trip occurred because of the column sump level low-low trip. The table and the chart tell us that the outlet pump stopped 3 seconds after the trip was initiated, which was within the 5-second target time. We can confirm that this actuation is a valid test. The cause verification page is used to select the parent SIF that led to this child SIF being activated. The parent SIFs page confirms this relationship has been established. Returning to the SIF activations page shows us that the column sump level low-low and reflex drum level low-low trips have both been verified and tested, as well as showing the parent-child relationship. Moving to the initiating causes page provides users with a list of initiating causes. The page's primary function, though, is to identify initiating causes which have exceeded their expected design frequency. The filter pane allows users to filter data contained in the content pane based on time, plant hierarchy, and several other filters. In this instance, we are going to apply a filter to select only those SIFs that are associated with the column. We are specifically interested in the column sump level low-low trip and the level control valve fail open initiating cause. This has been the initiating cause for this SIF on 3 separate occasions. The design frequency for this initiating cause is once per year, and it is currently in an amber state. This is because the calculated frequency is at 67% of the design frequency for this LOPA phase, remembering that the defined LOPA phase encompasses several years. The Maintenance Override System, or MOS, overview table tabularizes all configured SIF overrides into IL rating groups. These groupings display key aggregations relating to SIF overrides both currently and within the filter period. In this filter period, there have been 3 instances of SIL1 SIFs which were overridden or bypassed, but there are none currently active. Taking a closer look at SIF 005 in the safety system logic, we can see that this SIF is not currently overridden. I will now activate a MOS on the engineering workstation and demonstrate that SFM recognises and records the SIF override. SER records the moment that SIF 005 MOS is activated. The MOS overview table shows that a MOS is currently active and that in this filter period there have now been 4 instances of SIL1 SIFs being overridden. I will now deactivate the same MOS on the engineering workstation. SER records the moment that SIF 005 MOS is deactivated. The MOS overview table shows that the SIL1 SIF 005 is no longer currently active. The Integrated Control and Safety Systems Independent Layers of Protection, or ICSS-ILP, overview table shows independent layers of protection such as alarms and controllers, which are not operating as per design intent currently and at any time during the filtered period. The ICSS-ILP overview table tabularizes all configured ILPs into IL rating groups. These groupings display key aggregations relating to ILP inactivity both currently and historically. Clicking on any IL cell will redirect the user to the ILP report page where the appropriate data pertaining to the selection will be displayed. In this filter period, there have been no instances of ILPs being inactive and there are none currently inactive. Taking a closer look at SIF 001 in the safety system logic, we can see that ILP1 of this SIF is not currently inactive. I will now deactivate an ILP on the engineering workstation and demonstrate that SFM recognises the ILP has become unavailable. SER records the moment that SIF 001 ILP1 becomes inactive. The ICSS ILP Overview table shows that an ILP is currently inactive and that in this filter period there is now one instance of the ILP of a SIL2 SIF being inactive. I will now activate the same ILP on the engineering workstation. SER records the moment that SIF 001 ILP becomes active. The ICSS ILP Overview table shows that the ILP is no longer inactive. You can navigate to the Reports page by clicking the Reports option on the main menu. The common reporting features include printing, exporting data, filtering and searching, data paging, and column sorting. A report is selected by choosing one of the options from the drop-down list in the sub-menu of the Reports page. This includes the overall SIF report, SIF input report, SIF output report, independent layers of protection report, trip inhibits and overrides report, and the parent-child relationships. These reports are designed to address the requirements dictated by IEC 61511. The standard states: discrepancies between expected behaviour and actual behaviour of the SIS shall be analysed. The overall SIF report displays SIFs as they would appear in systems such as TRAC. Each SIF contains several subsections containing aggregated, associated SIS information such as actuating devices, initiating cores, ILPs, and MO data. The overall SIF report's primary function is that of analysing SIF information which took place versus what the LOPA design expected. This will aid subsequent design reviews. The standard states: operation and maintenance procedures shall be developed in accordance with relevant safety planning and provide a procedure for collecting data related to the demand rate and SIS reliability parameters. The SIF input report displays a list of SIFs with the associated SIS data, such as number of SIF activations, percentage of time SIF was in MO, and number of MO occurrences. The standard states: at some periodic interval, determined by the user, the frequency of testing shall be re-evaluated based on various factors including historical test data, plant experience, and hardware degradation. Note: the user can adjust the test frequency based on this data and an analysis of the original basis for test frequency. The SIF output report displays a list of actuating devices and associated SIFs. The main purpose of the report is to assist in daily maintenance activities, identify device actuations which can be used as test replacements, track device actuations which have been marked as test replacements. The standard states: management of change procedures shall be in place that identifies changes that will affect the requirements on the SIS. For example, redesign of the BPCS, changes to manning in a certain area. The independent layers of protection report displays the number of occurrences and percentage of time an ILP was not working. The standard states: the status of all bypasses shall be recorded in a bypass log. All bypasses need authorization and indication. The trip inhibits and override report displays all SIFs which have been in MO. The parent-child relationship report displays the SIF activation relationships between SIFs. This identifies what SIFs cause an initiation of other SIFs. This report can be used for tracking of SIF relationships to ascertain that the masking is appropriate. As mentioned earlier, functional safety doesn't end with the construction of a safety instrumented system. Monitoring and assessing continue for the life of the plant. Yokogawa's SFM makes it easy to produce the reports you need to see clearly and assess what is happening in the plant. This will help you meet the requirements of the IEC standard. But it's about more than just meeting a standard. Through monitoring and assessing your safety instrumented system with SFM, you'll be able to be safe and proactively improve your business and your production processes. At the start of the video, I asked the question, will your safety system keep you out of the news? Can you confidently answer yes? Thanks for watching this video. Be sure to check out the other videos from Yokogawa, Australia and New Zealand.